Hey, thanks for having me here. Appreciate it. Try to make this, relatively high level. Try to keep it somewhat engaging, but basically just gonna go over kind of FHE, different like crypto primitives, I guess. Been hearing these talks for the past like I don't know, whole day, afternoon. So let's just dive into it. Yeah, but real quickly, if anyone's interested, we're working on like an FHE L2. So essentially, it's a way to use like fully homomorphic encryption on an L2. What the fuck does that mean? We'll actually get into that in a few slides, but just start here if anyone wants this, or else just hit me up later. Yeah, also for any developers that are interested, here's just kind of like a quick cheat sheet to like, get involved. But let's just dive right into it. Um, Okay, so what is fully homomorphic encryption? So I'm sure people are probably interested in privacy. I know a lot of times when you talk to people about ZK, they're like, why interested in ZK? It's like scalability, sure, but a lot of times it's privacy, right? So fully homomorphic encryption is kind of like this term of, being able to do operations over ciphertext without decrypting. So essentially, you want to be able to kind of interact with like two hashed values, if you would, and kind of get like the output of these operations. And like the actual response of what it should be, but being able to keep that output private. So the concept of homomorphic encryption is sort of the ability to do, some things and keep their integral structure. So when you think about it like homo and like homomorphic, right? Homo is in like, like a homosexual, like same thing, kind of like keeping one to one, and then in the morphic is sort of like the change, right? So it's kind of like what you do to like a plain text should happen to a ciphertext, right? If you kind of think of it that way, keeping its structure. And fully homomorphic encryption is basically the ability to do like an arbitrary amount of computations on top of one specific ciphertext. Um, Yes. Okay. So basically, I'm sure some of you guys have heard like this LARP or like whatever it's called of like we got end-to-end encryption or like Tor was super good, like no one's gonna catch us, but like oh the NSA is like 51% of the servers or something, and then it's kind of just like okay, so we're just like trusting Apple, they're not gonna like decrypt our stuff and then just use it on their server because they're gonna have it, right? You get sued, something happens, legal, the NSA comes up to you, it's like no, they're gonna subpoena it, they're gonna get it from the database, they have it, right? That's why these leaks happen. So ideally, when you would think of end-to-end encryption, you would think that when you run a function, that function, whatever it's going to call the operation on the server, is basically going to not have to decrypt your values once they actually get those values to run it. But that's not how the world works, right? That's why you have these data breaches. That's why you have all these issues. So when you kind of think about how this would work, damn it, how this would work, like if we were to use fully homomorphic encryption, essentially like it would be client side, right? Kind of in the same way when you're using ZK, you construct a proof locally and then you submit that wherever. So it's kind of similar here where you are constructing like your own known values of the ciphertext in this case, or whatever your inputs are, and then the server is actually going to be able to run these numbers. So basically it's like, let's say I pass in encrypted number 5 and encrypted number 6 goes to the server is going to be able to like add these numbers together without ever seeing either of my input values, and like somehow the corresponding ciphertext here is going to be the sum of 5 and 6. So yeah, but here's kind of a quick overview. So like I like to think of it in some aspects, like don't shoot like, painting with a broad brush here, but like FHE is sort of similar to like where ZK was, like kind of in 2020, just in a sense where this is probably like the first time a lot of people are hearing about it. It's still very theoretical. We don't have like production ready applications. It's still kind of theoretical, waiting on hardware, waiting on X, Y, and Z things. But anyways, to kind of go over like a high-level overview of like fully homomorphic encryption is the idea of privacy homomorphisms have existed, realistically since like RSA was kind of introduced. That is a form of privacy homomorphism. But anyways, these seminal works were released in the 70s, and for about 30 years there was like effort to try to figure out how many of these operations we could pack in. So when you think about like homomorphic encryption, it uses something called like noisy encryption, which is kind of just like throwing in some bullshit with the truth to like make sure that people can't just know exactly what you're doing, right? It's why you bluff in poker, so that every single time you fold, you go in. If you go in and you're not bluffing ever, then people are going, you got the nuts, they're gonna fold. So sometimes you just gotta add some of this noise. Issues with that is when you do multiple operations on the same ciphertext, you want to keep adding arbitrary values non-interactively or however you're going to do it. Eventually that noise compounds, it cascades, and it becomes an issue. You no longer get to the point where you're able to actually decrypt back to the original plaintext value. So how do you kind of solve this? So in 2009, this guy, Craig Gentry, came up with this concept called bootstrapping. Bootstrapping is sort of a way of, you can kind of think of like recursively kind of having this decrypt reset where you sort of checkpoint like what the noise is, which is kind of a fancy way of saying that you're making the size of the ciphertext essentially constant, right? So now you're going to be able to scale to arbitrary computations. Trade-off is obviously it's expensive, boom, from there, there's been all these like branching FHE schemes. Some are more like, include like leveled schemes, which is like kind of like float into that, operating over flow. Some people will say, hey, that's better for like machine learning AI. I don't know, but like, that's what people say, and there's a lot of different takes. But at least for us, one of the branches that we're using right now is this thing called like TFHE, which is like the fast bootstrapping branch. Has like Boolean circuits, etc. But it allows you to kind of reset arbitrarily. It's programmatic in the sense where like, okay, now you can actually have these specific ciphertext values that you can like reset the noise each time. So it's kind of useful for blockchain in some aspects. However, like I said, level schemes have their application. For example, if you're going to be underneath the noise threshold, then why not, right? If that specific ciphertext doesn't need to exist forever, if in a way it's almost ephemeral. But I won't go into too much depth here, but it's somewhat interesting, I suppose. All right, so I'm sure a lot of you have kind of heard like the concept of using like ZK for privacy, mostly when it comes to on-chain stuff, or like ZK's endgame, etc. Like, I definitely do think that like ZK for endgame for like constant time verification or just like proof of computation or atomic settlement, whatever, like that's fair. Privacy, I think, is sort of like its own issue. You know what I mean? Because like a lot of times, like kind of like what Alex was just saying too, like a lot of like when you're using these ZK stuff, a lot of it is like kind of what are you really verifying? Sometimes you're verifying like an MPC procedure, for example. So they're compatible. You can use FHE and ZK. For example, you can use like ZK to verify FHE operations, proof of ciphertext formation, and something like a ZK POK, like a proof of like a zero knowledge proof of plain text knowledge. But either way, the main issue here is that like if you try to have multiple inputs, adversarial inputs, right, it's going to leak to the prover left to its own devices, right? Because the prover itself is going to have to generate based off these inputs, and then we've all heard the thing where you can like prove information without having to reveal the information. But what if there's multiple inputs of this? Like, where do you get the composability, right? So in that sense, like ZK is kind of limited by ability to manage a shared state, right? When you think about it, a lot of these applications come to like time lock, they come to some sort of like commit reveal scheme or something like that, but so it's kind of like two different tools, I feel like, for like the same goal. In some aspects, I kind of feel like ZK, like FHE is sort of like what we thought ZK would be for like privacy in some aspects. I mean, painting with a high broad brush here, obviously there's a lot of nuance and that's not exactly one-to-one. But so if you don't take anything else away from this like talk, I guess, just try to remember that like FHE is a way of running these operations over ciphertext without having to decrypt. And I guess unlike MPC, it's not interactable. We'll get to that in a second. So again, like ZK is kind of good if it's just your data, right? If you're just trying to prove something client side, it's your shit. Like, who cares? Like, what am I gonna like leak my own stuff? No, it's like my private thing. It doesn't really matter. But if you try to do it from like multiple parties, that's where things can get a little sticky, right? Okay, so here's like from a high level overview, kind of like the difference of sort of like the main like buzzwordy like here the privacy primitives are using and like kind of get funded and like shill or whatever. But like essentially there's TEs. I'm sure some of you might be familiar with, like it's sort of like a trusted enclave, kind of like a hardware solution to this. Obviously, it's kind of been, I guess you could argue it's sort of been the one that's been used in blockchains for a while. I mean, not talking about something more just like transfer specific like Monero or Zcash specifically, but like if you think about something like Secret. But anyways, like there's always going to be some sort of like known attack vectors with this, kind of like side channel attacks or just like issues with like the manufacturing. So like you kind of want to go to more of like a cryptographic approach, I suppose. And like MPC, like again, like the presentation we just saw, like again, if you can do these like additive secret sharing, theoretically you should be able to like mimic any function issue here is like, the interaction, because fundamentally communication bounds, which opens up latency issues, which opens up scaling issues, and generally you want to aim for non-interaction, right? That's why we talk like ZK, like for example, like snarks are like the end game of scaling, right? Part of it is because it's non-interactive verification, constant time verification. So then you go on to talk about like, we've already kind of talked about ZKP. It has like some niche use cases. Specifically, FHE is more general, right? Like you can essentially interact with all this stuff without necessarily need to decrypt. So from there, you're not leaking plain text to memory. And again, if you take nothing away from this, you're running operations over ciphertext without decrypting, and it's not interactive. So kind of just like, how do these sort of differ? So, okay, assuming ZK is more of a verification tool and we go to like the privacy specific things, which is like, like FHE, MPC, or like SGX, an example of a trusted hardware. But like, if you try to go for something that is like cryptographic security, which I think, it's blockchain. We always want like cryptographic security. I don't know if that's LARP, but that's what people say, right? So then it kind of comes down to really the way I see it when it comes to homomorphic encryption or MPC, which are kind of like the two things you can kind of decide between here. It kind of comes down to your interaction, right? Because like you like if you want to have a shared state for something, right? Like how are you going to scale that out to like 1,000 users, right? You try to create a fully dark like AMM, and not like the like fake whatever AMM, like private AMMs we have here, where it's like, okay, let's like create this like obfuscation in the transaction. And it's basically a time lock, and maybe there's like some additive homomorphism or whatever. But like no, like actually have the state. You have multiple state transitions, the multi-party inputs. All of this is over some sort of encrypted field that doesn't leak. Right. So then, but if you think about MPC, MPC is very important, right? Like we'll get to that in a second about how it's used in our stack. And you can kind of churn the issue that it is communication bound, or like that it into a feature, not a bug, right? Use that for like something like anti-collusion, for like, you know, has been said multiple times, like threshold decryptions. But anyway, it's kind of a high level. So what are we trying to do with like why the roll-up approach? I mean, I guess we're here. We're probably all like, at least to some degree, Ethereum fans. I guess we're fans of this like scaling mechanism. So that we're trying to do via the L2s. So, you know, at least from a high level, here's kind of like what the architecture could look like, right? So we're building like the first like FHE rollup. We're basically like these encrypted inputs for these transactions are kind of submitted to the sequencer. The sequencer, you know, is going to order them. Handle the executions, and then, you know, if the certain like opcode, for example, or the precompile that's going to get hit specifically for like some sort of decryption, right? That's going to be MPC bound. Although the other like FHE operations are going to be able to, you know, be more concurrent. They're going to be non-interactive. So. But we'll get to the threshold network in a second. It's an important component of like, you know, what you hear of like threshold FHE, and TFHE is not threshold well, it's a weird thing. It's but TFHE, if you just think about like threshold FHE in this case, like in actual practice. But again, we'll get to that in a second. So like any L2, we're just going to settle to the L1, and post-execution validators can submit a challenge for week. Submit a challenge for week. What does that sound like? Optimistic verification. So why are we using optimistic verification versus like ZK, right? Like, you know, I don't think we fundamentally disagree with the concept that like, you know, down the road, ideally we would want all this execution to be done, you know, via ZK. You know, it's just, but like in terms of like the overhead of like the proof generation and all this stuff, like it's just not really feasible to be verifying these FHE operations, multiple FHE operations in a transaction, multiple transactions in a block, into a commit, whatever, right? That's not the most scalable approach right now, and I kind of see it sort of like how the initial rollups were like Arbitrum, right? You know, the first rollups were optimistic, and now we're kind of getting like the ZK rollup. So I do think it's only a matter of time, in my opinion, until like all this stuff is be able to be verified. That's sort of like the end game in that aspect. But for now, we're kind of just playing with the, you know, technology of our time, the physical limitations, etc. But one of the things that makes me very bullish on you know, FHE hardware acceleration in general is that a lot of it is like funded by the government, such as like DARPA, for example, just because, I don't know, I guess the US government thinks the solution to like the quantum proof, you know, end game for that, I guess, and making sure like some secret thing doesn't like accidentally just like attack America in some aspect, because it's like, or anywhere really, just because like maybe they're like secretly like 10 years ahead of like whatever quantum computing stuff they said they would have, because, you know, it's based off of like the hard lattice problem instead of like, you know, based off of like prime factorization. So in that aspect, it's based off like the shortest vector security assumption. But anyways, that's kind of beside the point. So why are we specifically building like FHE OS here? It's kind of like, I guess you could say, like the secret sauce of like what we're trying to add to sort of the stack. So the important thing is, you know, to add like be able to have the ability to add different FHE schemes down the road. You don't know what's going to advance. You don't know what the hardware is going to be. You don't know what the use cases of blah, blah, blah. There's so many factors. So it's good to just be composable. Right, like who's to say that like maybe FHEML becomes a big thing because people want privacy for like whatever inferences, training, whatever, and then it ends up being like some scheme out of like Korea that's just like, you know, we're fitting all these operations in like one bootstrap, and it's like, okay, like that's what we're doing now. So who's to say? Lots of things could change, lots of things could be whatever. So threshold network. Kind of was talking about this threshold network, right, where I'm sure some of you who are familiar with FHE might be familiar with the concept that some people are saying, oh, it's MPC bound. I think that's kind of true, not necessarily true. And I say that's not necessarily true because realistically, if you're trying to like actually build something like this ongoing state like you would in like Ethereum or an L2, whatever, right? Like if it's just the FHE operations themselves, you don't necessarily need to go through the decryption network, right? You only need to go through the decryption network if you're actually trying to decrypt something, and, you know, under the hood, nonetheless. And so from there, you kind of have different assumptions, but if you're just purely doing FHE, which is kind of the way that like, for a few reasons we'll talk to in a second, but basically, high level, when you're working with FHE, I think it's generally recommended to make sure that you avoid any decryptions, because decryptions in general are going to leak plain text to memory, but again, we'll get to that. And also, you're just going to have to deal with these like MPC issues. And the way we're trying to build this is we're trying to, there's a lot of issues with like MPC, kind of like honest majority or whatever, or like the whole spectrum of where you want to pick it. But you can essentially also have the option of making it so that you can deconstruct a specific field to make sure that it actually takes like one specific signature. It could be your specific signature. So in that case, like how could you theoretically collude against that? Because a lot of people will say that like, oh, a threshold network attack is theoretically more vulnerable in some aspects, because at least if you're doing like a 51% on a normal blockchain, it's a write attack versus this like theoretically could be like a read attack. So you can kind of think of it like, I don't know, when the Allies like crack Enigma, you don't tell the Germans you crack Enigma, right? You just like do whatever and you bust it out when you need it. So like it's a theoretical thing where it's like hard to trace. But yeah, again, you're going to do this with the re-encrypts as well, but we'll get to that. I won't touch too much on that. So again, the fraud proofs with FHE, relatively straightforward. Again, this is just kind of a way that we are building out our stacks. So maybe some of you that might be familiar, like conceptually, with something like Arbitrum Stylus, which is kind of like where you have these two VMs. You have the EVM that sort of like can connect with like another virtual machine. This is like, for example, like currently our FHE operations are in Rust, right? So that's not going to run in like Solidity. So you need like some sort of precompile that's going to be able to talk to another VM, and then both of those are going to compile down to a format that can be verified by the L1. So that's just kind of like from a high level, it's sort of just like stack construction, but again, kind of beside the point. But anyway, for the rest of this presentation is kind of going to be going over like building with FHE, like, forget all like that kind of high level whatever I was saying earlier, kind of getting into like how are we actually going to build this. So yeah, for those of you that are familiar with Solidity, we try to take the approach of like, okay, let's make this as like, I hate this term, but like as simple as possible, or like try to like remove the developer friction when it comes to like just building out FHE projects, right? We're not expecting you to learn another language or like do all these like ceremonies or like whatever, like this command, like do you have to do this into your client, etc. Like should keep it relatively simple, right? Like why not just keep it as an import? Why not let people use the tools that they're already using? So from a high level, for those of you that are interested, I don't know if, some people prefer to use like hard hat, but we have we have the ability to create kind of like a local instance here. You can also use Remix. I don't know if people still use Remix, and I guess more people are using Foundry these days. So, we're currently working on Foundry integration. It should be out by next month. So things are pretty good. I've been playing around with it. All right, so inputs. So from a high level, like why try to reinvent the wheel here, right? Like when you think about a smart contract in Solidity, right? You have things like unsigned integer, like a uint 8, right? An unsigned integer bit length 8 represents any number from any integer from like 0 to 255 here. Same thing if you go up to like 256. But essentially, like that number's queryable, right? Pass in as input, write that to state somewhere, send that amount of money to someone in a transaction, like boom, that's visible. It's queryable. Everyone's gonna see what you're doing. Okay, so we just create this new data type that's kind of like an EUint 8. So it's an encrypted unsigned integer bit length 8, right? So again, it's kind of like this, like you could think of it like arbitrary bytecode, a hash, whatever you want to call it, a ciphertext. But essentially, it is like a hash, some arbitrary stuff you can't really decipher, but that still represents the number. So instead of just like passing in the number 5 to your contract, now you're passing in like the ciphertext value of 5. And it's relatively straightforward. You can use it as a value, as a lot of things that you can use unsigned integers for in Solidity. Now you can use an encrypted unsigned integer, right? So if you want to like send someone a value of like 5,000 Dogecoin or something, or like encrypted Dogecoin or whatever, now you can kind of just send that. Now it's not going to be able to really track, and you'll say maybe the address is leaked. Well, there's a lot of like kind of fancy ways you can get around that with like whatever, but that's again kind of beside the point for this presentation. So here's just kind of an example of how you can pass in like these new data types, if you would, into your function, which is relatively similar. So one here is just an EUint 8, which is kind of what it sounds like. It's like the input value of an encrypted unsigned integer bit length 8. And then you can also just pass in like arbitrary bytecode if that's the format, for whatever reason you prefer. Okay, so one of the trickiest parts I will say with like working with FHE is that it kind of operates like constant time code in the sense where you don't really have like classical branching. I'm sure all of us are familiar with the concept of like this, the if-else statement. It's like really programming 101, but now that's something that like isn't really feasible, like I said, because of like this inability to branch. So an alternative around this is sort of kind of using like a selector method, which is kind of like a multiplexer, if you guys are familiar with that. But essentially, it takes an encrypted boolean, and then it will do conditional assignment to like A or B. So I like to think that in FHE, with this constant time code, you don't necessarily have conditional write. You can't necessarily like only write to A if so and so, but it's like assign this value to A if whatever. So it's like conditional assignment without conditional write. So like it is a little bit annoying, but like you could theoretically still get the job done. So here's just a quick example where you're basically checking to see if A is less than B. These are encrypted values, by the way. So it's like A is less than B, and then if A is less than B, then that's going to give you an encrypted boolean. And encrypted boolean is basically exactly what it sounds like. It's what you think it would be. It's basically just encrypted, whether it's a 0 or 1. So it could be 0, it could be 1. So then you run the selection method, which is basically going to take this encrypted boolean, and if the encrypted boolean value is going to be true, it's going to assign it to A. If it's false, it's going to assign it to B. And then from there, you can kind of have your own like sort of conditional logic. Require statements. So require statements are a little bit annoying because like technically it's a decryption under the hood, so you're going to be bound by the MPC restrictions. But in some cases it doesn't matter, does not matter, and we try to handle it so like we still have asynchronous. So we're handling these decryptions asynchronously. Just a high level I should have talked about this in the threshold slide. But essentially you do this so that so the actual transaction itself doesn't actually halt the blockchain, right? Because there's all these issues with MPC, right? Like maybe one of the validators that you need to actually do XYZ thing just goes offline, or whatever happens. It could be a myriad of things. But also, like, we try to avoid this by making it programmatic, like who you actually want to handle these decryptions, and you can even use like a trusted execution environment with MPC to like make sure that like, okay, like these are the people that are actually running things, and if you have more of a trusted setup in that aspect, maybe you don't need to necessarily do such a high number of rounds. You don't need 80%, maybe you could do 60, maybe you can do 40 if you really just, depending on like the sensitivity of like that specific value. But anyways, from a high level, right, like the require statement here is going to allow you to essentially revert this function, this transaction if the requirements aren't made, right? Because you want a way to essentially be able to have like this, reversion without having to actually reveal anything. Obviously, if you think this through, it might give you like a conditional like binary, like okay, pass, didn't pass. Result, but then when it comes down is like how you construct your code, how do you make sure that that result doesn't actually leak anything that's necessary to state. So that's just kind of a design another thing that to keep in mind, to be cognizant of when you're designing stuff. And so conversion leakage. Okay, so basically I like to think about it this way, that like if there's ever a trace of something somewhere, then someone's gonna find it, right? Like when you decrypt, when you have a plain text, you're leaking plain text to memory, there's gonna be a stack trace, right? And when we're working with blockchains, right, there's a stack trace of basically everything, because it's all just like, like the state machine of it is basically going to go one step at a time. So at any point, here's just a really simple example, right, where you're passing in an unencrypted value, and then you're encrypting it, and then you're doing whatever. But like obviously, if you look through what happened, you're going to be able to see that like this initial value is passed in. So basically, you just have to be cognizant of the fact that like, if you have a private value, you have to make sure that at no point it was public, or else it's just kind of like, it's burned. It's like not something you can use anymore. So FHEnix.js implementation, JavaScript. Who loves JavaScript? But it's basically like we try to. I use this term, but again, we try to make it like simple, or as simple as possible, to like what developers are familiar with. For those of you that might have worked with something like Ethers in the past, it's basically kind of just a way of like interacting with the ABI, and that where like if you looked at that last function, where like basically using standard Web3 Solidity development, you probably just pass in the number 5 as your input to a function. But now if it requires an encrypted input value of that number 5, then what you're going to do is you're going to use this, which is really just kind of like one line of code here, where you're creating this like new instance data type, if you would, of like this encrypted value, this hash value of 5. And then you're passing that into your function as you would normally pass a plain text version in. So from there, it's all relatively the same, except for when it comes to view functions, some view functions. So what are permissions? Essentially, if you have a network and you only want a certain party to actually be able to view your stuff, right? Like I have a ciphertext, and I only want people that like I'm an OnlyFans creator or something, and like I only want people that like pay me my money this month, to actually get my newest nudes or whatever, right? So it's like, okay, like I want to make sure that I have some conditional logic, so only a specific like pub key, only a specific address user is actually going to be able to decrypt, to get a re-encrypt of this, a sealed output, if you would. So a sealed output is kind of like a stateless decryption that's wrapped with like a specific pub key. And if you kind of think of like this syntax here, it's sort of kind of like a modifier in the sense where you're essentially checking that the message.sender is the correct like permission access. This is the correct pub pub key to view this specific ciphertext, right? Because again, you don't want to be giving out your news for free, and etc. And other things, it could be your bank value or your medical stuff. I don't know why I picked that example, but yeah. So here's kind of like another example of how you do it in the client. I won't get into too much detail here specifically, but there's always a lot of options with things. Yeah, and again, so here is a simple contract, kind of just going over relatively how straightforward it is to work with FHE, how straightforward it can be, in the aspect where, we try to keep it as simple as possible. Why make people do all this, jump through all these hurdles and like learn an extra language if you don't have to, right? And ideally, I think things should be simplified, especially from an engineering perspective. So you look at it as just kind of a one-line import. Now you get these data types. Now you kind of add these data types. I feel like it's relatively not too different from how you're used to developing a smart contract, but anyways, so if anyone's interested in actually playing around with this shit, your blocks might start to overflow, and you'll be like, what the hell's going on? FHE is still expensive, I get it. We're still waiting for the hardware, still waiting for all this stuff to improve. So, the things to remain in mind, at least, like, I think right off the cuff, you're having these overflow issues, right? It's just like, okay, think about what you're actually doing here. If you look at our docs, you can see, like, the total amount of operations you can actually fit into each transaction. So for each block, but basically just to be cognizant of like certain functions, certain operations are going to be more expensive than others. Like adding 2 ciphertexts is going to be cheaper than like dividing 2 ciphertexts. And then bit length also matters, right? So basically adding 2 8-bit numbers is going to be a lot cheaper than adding 2 like 32-bit numbers. So these are kind of just like design constraints that are very important to be cognizant of if you run into this issue. Yeah, and so here's kind of the tip, like, ChatGPT is, like, low-key kind of based with this. Like, you would think, like, hey, it's kind of new, not all the people using it, maybe it doesn't have a training data. It's not bad. Like, it produces some stuff, like, kind of gets it working a little bit better than you'd think. It still has some, like, weird, like, AI, weird syntax bug things sometimes. But, like, for the most part, it's like, paint with a broad brush, why not? Yeah, so that's basically it. That's my presentation. Yeah, thanks for having me.